sleepy people post-lunch, well, I'll do my best. This is only a 10-minute talk. So hello, my name is Joyce. I'm in town from San Francisco. I work for Viam. I'm the head of developer relations for them. It's an open source platform for building physical AI. So some people probably think that computer vision is pretty much a solved issue by now, but getting CV to work in real time at the edge is still an issue. So why do CV pipelines fail when you bring them into the physical world? They work great on your bench, but once you bring them into the wild, why would they fail? Well, it's slow, it's expensive. You might be working with low power, low bandwidth devices, and of course you have concerns with working in the cloud. Here's an example, VLMs. You might not be able to see that from the back, but if you upload an image or a video stream and ask it to describe what's happening here, it's pretty slick. But VLMs are heavy, slow, and they require a lot of compute. Even something that's designed to work locally, like a Moondream, can take several seconds to respond. And that's really not good for real-time actuation if you need it. So if you need something to instantly turn on your lights, you don't want to be sitting there in the dark for a few seconds before it instantly turns on. Instead of throwing bigger models at the problem, we can optimize down and build leaner systems. So let's talk about 3 design patterns, starting with continuous local inference. We want to run the model locally and then only send events or metadata upstream. Here's an example. When shelves look empty, you lose revenue. Customers spend less money. I looked at a bunch of different stats, and it's around 25%, but it varies widely. And it turns out you're losing money not just from that item not being there, it's out of stock, but the appearance of scarcity actually makes everyone spend less. So how can we solve this with computer vision? Well, it doesn't really make sense to stream every single shelf to HQ just to monitor your stock levels. That's expensive and slow. Instead, you can run a lightweight model like YOLO. You only live once. It stands for you only look once. It watches the shelf and you're running inference locally to detect when items are running low. And then when you need to restock, it sends a signal. And you can also have local actuation, like a Kanban light. Kanban light comes up, and the human comes and then restocks the shelf, or a system-wide alert. So again, you're not sending your video upstream, only the event. Frigate is another open source example of this design pattern, very popular. In this example, it's also running YOLO locally, this time for person detection, and you can integrate it with Home Assistant to connect to the rest of your smart home for actuation. So Frigate does have a cloud tier. They're trying to make money, but it can entirely run locally. And beyond that, it can also run air-gapped, so you're completely offline. So the video stays local by default. The second scenario we have is sensor fusion. So you can use cheap sensors to trigger more expensive CV. Here's an example with endangered whales on the East Coast. That little red dot is an endangered whale, and all those blue things zipping around are huge boats that are coming to take out those whales. So to protect those whales, federal regulations have implemented a 10-knot speed limit for really big boats, which is effective. But now they're trying to expand that speed limit to smaller boats. I used to live in Denver, so I know some of the traffic around here gets a little gnarly. Take one of your main arteries, like I-70, make it a playground, slow children's zone. See how well that goes over. It will protect the children, but a lot of other impacts. Instead, how can we solve this with computer vision? Waves is an open source program using AI to detect whales. So when you're on a boat, you're actually relying on something like Starlink, and that can be a little spotty. And instead of running or streaming video or running full-time CV, you can use low-power sensors to detect when you're entering a certain zone or reaching certain conditions to trigger inference on demand. So you're saving on compute and also false positives, okay? Because you're marrying additional sensor information in with it. So how does that work? You have environmental sensors that act like a low-power watchdog. And when you cross a certain threshold, you can activate that camera. That camera's not running all the time, and then run the model. So again, we're using low-power sensors to manage our resources. And in the last example, scenario 3, we have edge-first systems designed to work fully offline. If you've ever been to a professional sports game or even a developer conference like this, I feel like the bathroom lines are pretty good here. But you've stood in a line like this. Just like that inventory example, it turns out if you're waiting in line, you're spending less money overall. So stadiums, they have a lot of cameras. We can solve this with CV. Here's a mobile app. On the right, you might be able to see, you can tell which bathroom has the longest line at that time. So you're not missing any of the game, and you can just head straight to that bathroom. It's called Quick Queue, but I wanted them to call it PQ. Didn't work out. But, okay, you're at a big stadium, it's very crowded, maybe you're experiencing this here, but really crowded stadiums don't always have good internet. So your app has to work locally, make those decisions locally. And so in this example, we're displaying wait times peer-to-peer, and then when you're ready, and only if you want to, maybe it's at the end of the day, maybe it's at the end of the game, maybe it's in the middle of the night, you can sync to the cloud for other kinds of analytics, venue-wide analytics, and cold storage, if you want to. So the 3 examples that we talked about, for the inventory example, we were running continuous local inference and only sending event data upstream, being very shrewd. For the whales example, we use low-power sensors to trigger a more expensive just-in-time inference. And we were able to manage our resources a little bit more smartly. And then for the bathroom lines, everything runs fully offline. And if you want to, and only if you want to, there's an optional batch for stuff that's not time-sensitive. So for most of these examples, we were using YOLO running on a TensorFlow Lite runtime, which is optimized for single-board computers. It's also lightweight enough to run locally and accurate enough to drive decisions. And if you're worried about accuracy, you can, again, marry it in with other sensor data. And actually, if you want faster inference, so that hardware accelerator is at the bottom there, the first column, you can use stuff like Pi came out with an AI hat, or use something like Coral TPU, which is what Frigate generally recommends for accelerating your AI. For the data layer, for these examples, I believe we were all using gRPC for fast typed API calls and WebRTC for low latency peer-to-peer communication. And for orchestration, we were using Viam, that's a company I work at, for plug and play integration for different models, sensors, and actuators. So why does this matter? For these reasons. You can get started with something like a Raspberry Pi. You can scale it to an industrial fleet. You can run completely offline, which is good if you have issues with remote locations, and all using open standards and tools. So in other words, we can use event-driven architectures to do more with less at the edge. I know that's going to disappoint 2 of you right there because you were specifically interested in the streaming part. But it's practical, right? Why use a hammer when you don't need a hammer? So instead of scaling up with bigger and bigger models all the time, you can optimize down with event-driven architectures and lighter weight models. If you're just getting started with CV, I have a couple resources here. That first one is going to be a list of 5 projects that ranges from beginner-friendly to more advanced. So that Moondream VLM example I told you about is one of them. If you want to see how CV works with hardware, but you don't have any of your own, you can actually teleoperate a rover in the Viam robotics lab over in New York City. And for the 2 people that are sorely disappointed by how we got around with event-driven architecture, I did just publish last week in the gRPC community blog, that's the last one, an article called How Robots Talk, specifically about gRPC and WebRTC. So please come find me if you're building anything cool. I would love to argue with you or help you get started with some additional resources. So thank you very much for your time.